You ever stop and think about the magic that happens every time you plug something into the wall? I mean, there's this hidden translation going on, turning that wild, surging energy from the outlet into the calm, steady power all our gadgets need to work. Well, in this explainer, we're going to pull back that curtain and look at the brilliant, yet simple component that makes it all happen. Let's dive in.
So here's the fundamental challenge we're up against. On the left, you see alternating current, or AC. That's what comes from the power grid. Its voltage is constantly flipping back and forth, changing direction. But on the right, that's direct current, or DC. It's the stable, one-way flow that all our electronics, from our phones to our computers, actually run on. They're just totally incompatible. So our job is to somehow tame that chaotic wave on the left and turn it into that nice steady line on the right. This whole process is called rectification, and we're going to build our own rectifier right here, step by step.
To solve this problem, we're going to need a hero. And in the world of electronics, our hero is an incredibly simple but incredibly powerful component, the diode.
A junction diode has one job, and one job only, to be a one-way street for electricity. It's like a traffic controller for the circuit world, and its one simple rule, you can only go this way, is the absolute key to everything we're about to do.
This right here shows that one-way rule perfectly. When current tries to flow in the direction of the little arrow, we call that being forward biased. The gate just opens up and the current flows right on through. But if the current tries to go the other way, the diode becomes reverse biased. The gate slams shut and the flow is completely blocked. On or off. It's really that simple, and we're going to build everything on top of this one principle.
All right, so we've got our new one-way gate. Let's make our first stab at taming that wild AC wave. This first super simple approach is called half-wave rectification. Okay, let's check out the circuit. We start with our AC input, which goes into a transformer. You can think of a transformer as just a voltage adjuster, kind of stepping the power down to a level our device can actually handle. Then comes our diode, our hero component, followed by a load resistor. That resistor is just a stand-in for whatever we're trying to power, like the charging circuit in your phone. It's a really straightforward setup. So let's trace the flow of electricity. During the first half of the AC cycle, the voltage is positive. This puts our diode into that forward biased state we talked about. And just like that, the gate opens, current flows right through the circuit, and boom, we get our first positive voltage pulse at the output. So far, so good, right?
But then, remember, the AC input flips. During the negative half cycle, the voltage goes negative. And that immediately puts our diode into reverse bias. The gate shuts down, the circuit is essentially broken, and absolutely zero current can flow. So if you look at our output graph, it's just a flat line. Nothing's happening.
So what have we actually achieved here? Well, we did succeed in making the current go only one way, which is great. But just look at that output. We have these little pulses of energy, followed by these huge, empty gaps. We are literally throwing away half of the power that we're pulling from the wall socket. It's incredibly inefficient. We can do way better than this.
Okay, so let's move on to a much more clever, much more efficient solution that actually captures all of that energy we were just wasting. This is called the full-wave rectifier.
Now this circuit looks a little more complicated, but the idea behind it is absolutely brilliant. We've now got two diodes, D1 and D2. And the real game changer here is a special kind of transformer with a center tap. You can think of it as splitting the power source into two synchronized halves, an upper half and a lower half that are going to take turns powering our device.
During the positive half cycle, things look pretty familiar. The top half of the transformer is positive, which turns on diode 1. The current flows through our load resistor, and we get our first output pulse. Meanwhile, the bottom half is negative, so diode 2 is reverse biased, and it just sits there, turned off. Okay, now here is the really clever part. When the AC wave flips, the top half of the transformer becomes negative, which turns diode 1 off. But at the exact same moment, the bottom half becomes positive. This turns diode 2 on. And crucially, look at the path the current takes. It flows through the load resistor in the exact same direction as before. What this circuit does is it takes that negative half of the wave, the part we were throwing away, and it flips it upright into another useful positive pulse. It's genius.
And the result is this continuous series of positive pulses. See? No more wasteful gaps. It's so much more efficient. But we still have a problem. Yeah, the current is only going one way, but it's not steady DC yet. It's a really bumpy ride, right? A voltage that's constantly rising and falling.
We're close, but we need one more step to get that perfectly smooth power.
So how do we smooth out all these bumps? To get that perfectly flat, steady DC that our electronics are craving, we need one final step, and that step is called filtering. To do this, we bring in another fundamental electronic component, the capacitor. And the setup is super simple. We just place it in the circuit right alongside our load resistor. Its whole job is to absorb the peaks of those bumps and then fill in the valleys.
You can think of a capacitor as a tiny, super fast, rechargeable battery. So as the voltage from our rectifier rises up to a peak, the capacitor charges up, storing that energy. Then, just as the rectifier's voltage starts to dip back down, the capacitor kicks in and starts to discharge, releasing its stored energy back into the circuit. It basically props up the voltage, filling in that gap until the next pulse comes along to charge it back up.
Now, how well this all works really depends on how slowly the capacitor discharges, and that rate is determined by something called the time constant. It's a product of the resistance and the capacitance, which is why you'll often hear it called RC. To get that really smooth output like what you see in curve B, we need a large time constant. That means the capacitor has to give up its energy really slowly. And we do that by just using a capacitor with a large capacitance value. It's that simple. Bigger capacitor, smoother DC.
Okay, let's just step back for a second and look at the entire transformation we've just put together. From that chaotic AC at the wall to the calm, stable DC our technology relies on.
And here it is, the whole story in one picture. We start with our input AC, swinging both positive and negative. Then our full-wave rectifier chops off the bottom and flips it to the top, giving us that pulsating DC. Finally, our capacitor filter smooths out all those pulses, and what we're left with is a nearly flat, steady, power supply-ready DC output. It's a beautiful three-step journey from total chaos to perfect calm.
All right, so let's just quickly recap the key takeaways. The junction diode, that's our essential one-way gate. The half-wave rectifier was our first attempt, simple but super wasteful. The full-wave rectifier is the much smarter design that uses the whole AC wave. And finally, the capacitor filter is what gives us that final polish, smoothing the output into steady DC. And remember, its effectiveness all comes down to that RC time constant.
So, we've successfully tamed the current. We've created a great source of stable DC power. But this brings up a really interesting new question, doesn't it? A laptop might need around 20 volts, but your phone only needs 5 volts. How do we take this bulk DC we've just made and regulate it down to all the different precise voltages that our various gadgets actually require? Well, that's a whole other story for another time.